In some longer differential equations where the terms for each variable are linear, the method of coefficients linear to two variables can be used. Learn about this method here in Engineering Math 5. In the case of a long differential equation denoted as such, where the constants c1 and c2 are 0, and x and y are in their first degree, you can see that this is a homogeneous equation. In coefficients linear in two variables, the main goal is to simplify the equation to make it homogeneous. Let's analyze the same equation shown earlier. Both the derivatives dx and dy have a linear coefficient with them, and in this case, these terms are linear, meaning x and y are of the first degree. So we can understand these coefficients as lines. If we equate them into 0, we can determine if these two linear equations are intersecting or parallel. Such a check is used to know the method to process the general solution later. First, review how to check the terms if intersecting or parallel. Recall that when the coefficients of the variables are equal, then they are parallel lines. In contrast, having different coefficients will show that they are intersecting lines. And to know the intersection point, one can use substitution or elimination. In this case, we determine the point of intersection by substitution. Using equation 1, x is taken as 4 minus 2y, and that would be equation 1a. Plug this into the second equation, which can be simplified to give the value of y as positive 1. Use the value of y as 1 back in equation 1a to have x as 2. So the point of intersection is 2, 1, which states that 2 is h and 1 is k. These variables have been introduced in analytical geometry. In this video, we will focus on intersecting lines, the procedure of which is to start with the goal of simplifying the differential equation into a homogeneous equation by substituting variables with a point of intersection. After determining the homogeneous equation, another substitution is used to simplify the equation to be integratable when it turns as a variable separable equation. First example is to determine the general solution using coefficient linear in two variables with the function the quantity of y less 2 times dx less the quantity of x minus y less 1 times dy is equal to 0. Just like discussed, check if the lines are parallel or intersecting. And since they are indeed intersecting, determine the point of intersection by substitution where we get 3 and 2 for h and k. The next step is to use the point of intersection as part of substitution. Take x as u plus h, where h is 3, so x is u plus 3. The derivative of x is du. Do the same with y, where it is equated with v plus k, or that will be v plus 2. dy is also taken as dv. Note that the derivative of a constant will be 0. Plug this into the equation and then cancel constants, which can simplify the equation into v du less the quantity of u minus v times dv is equal to 0. If we eliminate grouping by distribution, it would be easily seen that the equation will be homogeneous. Do the second substitution using the concept of homogeneous equations, where you choose a variable and equate it with the other variable multiplied by a new one. The derivative of the chosen variable u is du, and the derivative of v times z will be using product rule, thus it will be v dz plus z dv. Plug these substitutions into the equation and expand to eliminate groupings. Cancel similar terms if possible to shorten the equation into v squared dz plus v dv is equal to 0. It is noted at this point that the formula boiled into variable-separable equation. So separate the terms and collect similar variables, which leaves us with dz is equal to negative v dv all over v squared. Cancel v from the numerator and the denominator to have dz is equal to negative dv all over v. With a simple equation, we can readily integrate it to arrive at z is equal to negative ln of v. With integration done, we can revert back the substitutions earlier. Start with the latter substitution of u is equal to vz, taking z as u all over v. Plug it into the equation to have u is equal to negative v times natural logarithm of v. And revert back the first substitution made where x is u plus 3 or u is x minus 3. Do the same with v as y minus 2. Place them in the equation to have x minus 3 is equal to negative of the quantity y less 2 times the natural logarithm of y less 2 plus c. By using the rules of logarithms, we can simplify ln in the equation to have x less 3 is equal to the quantity of 2 less y times ln of c times y minus 2. The second example requires the general solution using the method in the function, the quantity of 2x minus y times dx plus the quantity of 4x plus y less 6 times dy is equal to 0. Start checking the lines where we have intersecting lines once more. Using substitution, we should determine the point of intersection where we get hk as 1, 2. Then have the first substitution where x is equal to u plus h, or that is u plus 1. Y is equal to v plus k, which is v plus 2. Their derivatives should also be taken. Now plug all the substitutions into the equation and expand those with parentheses to be able to cancel the constants, leaving with a shorter equation of quantity of 2u minus v times du plus the quantity of 4u plus v times dv is equal to 0. Take note at this point that we arrive with a homogeneous equation. Solve using the concept of homogeneous equation by substitution where we choose v in terms of the other variable u multiplied with z. So the derivative of v is dv, which is equal to u dz plus z du by product rule. Plug the replacements into the equation. The second term would require FOIL method to be simplified, leaving us with the longer equation. If we regroup the terms according to similar derivatives, we come up with the following equation, where it is also noted that each term in each group has similar terms which we can extract again. By doing that, we get u squared times the quantity of 4 plus z times dz plus the quantity of 2 plus 3z plus z squared times u du is equal to 0. If we move the other term into the opposite side of the equal sign, we can note that the resulting equation is a variable-separable equation, so collect similar terms and then again simplify u all over u squared, making the right term as a negative of du all over u. However, the left term is somehow more complicated. How do we integrate 4 plus z all over the quantity of 2 plus 3z plus z squared? We need to simplify the denominator to z in the first degree. The simplification is done through integration by partial fractions. This is the method of identifying the equivalence of the term with the introduction of some variables. The denominator can be factored into z plus 1 and z plus 2, which will be separated. Now take the LCD and multiply it to the whole equation. Thus we get 4 plus z is equal to a times the quantity of z plus 2 plus b times the quantity of z plus 1. If we want to zero out b, we equate z as negative 1 to have the value of a as 3. Next is to zero out a by using z equal to negative 2, and b comes out to be negative 2. So the equivalent equation of 4 plus z all over z plus 1 times z plus 2 is 3 all over z plus 1 plus negative 2 all over z plus 2. Use this equivalent as replacement of the first term of the equation to have 3 all over z plus 1 plus negative 2 all over z plus 2 all multiplied by dz is equal to negative du all over u. Distribute dz among the two terms and now we are ready to integrate. The integral of 3 dz all over z plus 1 is 3 ln of z plus 1. The integral of 2 dz all over z plus 2 is 2 times the natural logarithm of z plus 2. And the integral of du all over u is ln of u, then we add the constant c. With ln present in all terms, use the rules of logarithms to simplify the equation. Recall that a constant preceding the natural logarithm is actually the exponent. And to simplify the right side of the equation, addition of logarithms is multiplying terms and subtraction is dividing terms. At this point, we can cancel the logarithm from both sides to have the final equation. Now revert back the second substitution involving v is equal to u times z, which makes z as v all over u. Transform the terms into one common denominator and separately use the cubic and square exponents to the different terms. It would be noted that we can cancel out the denominator from both sides, which would leave the equation the cube of the quantity v plus u is equal to c times the square of the quantity v plus 2u. With the resulting equation, revert the first substitution equating z with u and u with v. By plugging these values, there is not much to work on as they are simply enough, so just collect the constants to give the cube of the quantity y plus x minus 3 is equal to c times the square of the quantity y plus 2x minus 4, and this is the general solution for the given differential equation.